Yeah. Okay. So yesterday we built circuits, right? We built our own circuits. We had lights. We had a 9-volt battery, AA, right? And we made lights. We used motors. Okay. Today we're going to analyze how it works, right? How it works. How batteries work, right? Tomorrow, my goal is we're going to build our own batteries. Is it possible? What do you need? Find out. So tomorrow we're going to build our own batteries. So we've got to kind of get some background information. What is resistance, right? We use resistors. What's resistance? How do we figure that out? That's what we're going to go over today. Okay? Some background information. And then if we have time, I got some practice problems around the room we can try out. Okay? All right. So electrical current. Now, there are a few, I would write down at least the 2 equations that we're going to go over today. You don't have to. But it would probably be helpful. I know, we haven't done any math for a while. That's pretty crazy. All right, so to start off, we have electrical potential energy. So what is moving through the wires? What specific charge? Electrons. So electrons are moving. All right, so if you have two electrons close to each other, it's kind of like a magnet. What if you have 2 north poles close to each other? They repel, right? Or if you have 2 south poles, they repel. All right? It's the same thing. If you have 2 negatives close to each other, they're going to repel. And that's going to be high kinetic energy. All right? Talking about kinetic. All right? Whereas if you have 2 electrons very farly spaced, you're going to have high potential. Okay? Right? Because likes repel. That's the goal. Okay. Now, what is this potential difference? The potential difference we call as volts. Okay? So how much that electrons like to repel each other, we like to call as voltage. Okay? And you've probably heard that term before, right? That's voltage. Okay? All right, so in this example, I love examples. All right, so when you look at my copper wire, the current flow goes from here to here. So there's high voltage in here, right? Then you have your fan or a motor, something like that. It takes a lot of energy, right? And then when you guys get down here, there's not that much energy until you get back to the battery. Okay? And then you get more energy. You get high voltage again. Okay? Okay? Now, let's talk about batteries. Mind-blowingly awesome stuff. Looks so simple, right? You just go to the store, buy some AAAs. Simple. Easy. But they're so complex, right? Have you guys ever seen the, what were those called? The hoverboards that you float around on, right? Do you guys know why those aren't really existing anymore? They were exploding. Yeah, absolutely. Those little hoverboards, yeah, they kept exploding. That's pretty crazy. Now, on that simulation, were you guys ever having your battery turn fire? You on fire? Anybody get fire battery? No? You guys should have turned up the voltage a little bit. Your battery would have exploded. It's really crazy. So there is voltage across 2 terminals of a battery. Okay? So if you look at this, it's kind of hard to see. I have negative ions over here. Okay? On batteries, you have negatives and positives, right? So the electron current goes from here, and eventually it's going to go through there. Okay? Now, eventually all of the electrons are going to be over here. Now, somehow, some way, the electrons jump. They jump across the line, right? Because eventually these electrons have to come over here. So it literally jumps. And then repeats the circuit to keep the light working. Cannot believe how that works. But the electrons jump, right? Let's watch this TED Talk. Fascinating video. Have you guys ever seen TED Talks before? Pretty good. They're actually, I don't know if I've seen a bad TED Talk. All right. Here it is.
You probably know the feeling. Your phone utters its final plaintive beep and cuts out in the middle of your call.
Both lights will you fall asleep?
It may feel more like throwing your battery across the room than singing its praises. But batteries are a triumph of science. They allow smartphones and other technologies to exist without anchoring us to an infernal tangle of power cables. Yet even the best batteries will diminish daily, slowly losing capacity until they finally die. So why does this happen? And how do our batteries even store so much charge in the first place? It all started in the 1780s with two Italian scientists, Luigi Galvani and Alessandro Volta, and a frog. Legend has it that as Galvani was studying a frog's leg, he brushed a metal instrument up against one of its nerves, making the leg muscles jerk. Galvani called this animal electricity, believing that a type of electricity was stored in the very stuff of life. But Volta disagreed, arguing that it was the metal itself that made the leg twitch. The debate was eventually settled with Volta's groundbreaking experiment. He tested his idea with a stack of alternating layers of zinc and copper.
That's exactly what we're going to build tomorrow. Pretty similar,
separated by paper or cloth soaked in a saltwater solution. What happened in Volta's cell is something chemists now call oxidation and reduction. The zinc oxidizes, which means it loses electrons, which are in turn gained by the ions in the water in a process called reduction, producing hydrogen gas. Volta would have been shocked to learn that last bit. He thought the reaction was happening in the copper rather than the solution. Nonetheless, we honor Volta's discovery today by naming our standard unit of electric potential the volt. This oxidation-reduction cycle creates a flow of electrons between two substances, and if you hook a light bulb or vacuum cleaner up between the two, you'll give it power. Since the 1700s, scientists have improved on Volta's design. They've replaced the chemical solution with dry cells filled with chemical paste, but the principle is the same. A metal oxidizes, sending electrons to do some work before they are regained by a substance being reduced. But any battery has a finite supply of metal, and once most of it has oxidized, the battery dies. So rechargeable batteries give us a temporary solution to this problem by making the oxidation-reduction process reversible. Electrons can flow back in the opposite direction with the application of electricity. Plugging in a charger draws the electricity from a wall outlet that drives the reaction to regenerate the metal, making more electrons available for oxidation the next time you need them. But even rechargeable batteries don't last forever. Over time, the repetition of this process causes imperfections and irregularities in the metal's surface that prevent it from oxidizing properly. The electrons are no longer available to flow through a circuit, and the battery dies. Some everyday rechargeable batteries will die after only hundreds of discharge-recharge cycles, while newer advanced batteries can survive and function for thousands. Batteries of the future may be light, thin sheets that operate on the principles of quantum physics and last for hundreds of thousands of charge cycles. But until scientists find a way to take advantage of motion to recharge your cell battery, like cars do, or fit solar panels somewhere on your device, plugging your charger into the wall rather than expending one battery to charge another is your best bet to forestall that fatal bleed.
Okay. Fascinating stuff. Now, if you look at your phone actually tells you how much percent of your battery health is left, right? Backlight's coming on, 3, 2, 1. All right. So my phone's, I don't have it on me. My phone's a used iPhone 6, right? It's pretty old. All right. My phone only has 70% battery health left. So after plugging it in every day, over and over, the max I can get is 70%. That's pretty crazy, right? It's pretty crazy that, like, over time, the concept of our batteries die. All right. So, batteries, awesome stuff. We're going to try to build them tomorrow. Okay. Now, the current. The video kind of mentioned currents. All right. Now, the current, obviously, so it goes from a positive to a negative. Okay. So it's the opposite of the electrons, right? If we look at a battery, oh, this is terrible. I'm so sorry. If we look at a battery, there it is. So the top is always the positive, bottom's the negative. So all the electrons are down here, right? It's all in the negatives. Now, what happens when all the electrons are close to each other? Do they like each other? No, they want to get out. They want to be free. So the electrons are going to travel along the path, right? So electrons, I'm just going to do E's, they're going to be going this way, which means the electrical current's going to be opposite. Just know it's opposite. Okay, that's a big takeaway. Okay, the current is opposite. Okay, and we call that current an amp. Okay, you might have saw that on the assignment. We call it an amp. Okay, and just covered that. Okay, we good? All right. Resistance. Now we're getting into the math part of it. Okay, resistance. So yesterday we had resistors. Okay, what they do is they resist the energy. Right? They resist the current that's flowing. Okay. Now, this is the equation. That's one of the things I would definitely write down. Resistance is equal to the volts divided by the current. The voltage divided by the current. Okay, so the volt coming from the battery divided by the current. And the unit for resistance, it's a little interesting. The unit for this guy is ohms. It's ohms. That's the unit. The unit for voltage was just volt, right? That was just volt. And the unit for current was amp. Okay? Those were the units. All right, so some newer stuff we haven't covered before. Okay? So resistance. Let's try one out. Let's just try practice. Try practice. Okay. The headlights of a car are powered by a 12-volt battery. What is the resistance of the headlights if they draw 3 amp of current when they're turned on? What would we do here? 12 divided by 3. 12 volts divided by 3 amps. Your answer would be 4 ohms. Not too shabby, right? Not too bad. We feel pretty good on that. There's half our math. There's half our math. Okay. Do I have another one? I do. Let me erase that. Let's check this out. A 1.5 volt battery is connected to a small light bulb with a resistance of 3.5, that's ohm symbol, 3.5 ohms. What is the current of the bulb? What's my equation? Resistance is equal to what? Voltage over current. Okay, voltage over current. So I know my resistance is 3.5. I know my voltage is 1.5. Okay, so you can just flip-flop the 3.5 and the C. So C is equal to 1.5 divided by 3.5, which I don't know. Oh, I have a calculator. 0.42. Now, what's the unit for current? Amp. Very good. So 0.42 amp. Do we feel good on that? All right. Now, last part here. Oh, conductor insulator. Second to last part. Now, in yesterday's activity, there was things called, you put like a dollar bill in there, right? You put a paper clip in there, right? Did the dollar bill conduct electricity? No, it did not. So a dollar bill is an insulator. There was so much resistance, it resisted the flow of electrons. Whereas a paper clip, did the paper clip conduct electricity? That would be a conductor. It conducted electricity. All right, so conductor, insulator. All right, that's the difference between the two. Conductors, low resistance. Insulator, high. Okay, let's get to our second equation. So we already talked about how energy is associated. All right, here is high kinetic. Here's high potential. All right, how do we calculate that? We calculate it by this. Okay, so power is equal to current times voltage. Power is equal to current times voltage. This is the last thing we're going over. Okay. So current, we said, is measured in amps. Voltage is measured in volt. Now power is measured in watts. Okay. Bless you. Okay. Let's try one out. Try one out. Okay. Let's do the top one. What is the power rating of a hair dryer that is plugged into a 120 volt outlet and has a 9.1 ampere current? Okay, well, watts is equal to my amps times my volts. Okay, so my amps, I know my amps over here, right? 9.1. That's going to be multiplied by my volt, which is 120. So your answer would be 1,092. 1,092, and the unit is watts. How do we feel on that? Pretty good? Okay. Let's see. That's all I got. That's all I got. Okay. So, what I want you guys to do